Can you hear me? There we go. Hello, everyone. So happy to see so many faces here today. It's always a pleasure coming back to Trondheim, talking about technology, my old student town. If you haven't been living under a rock, you might have noticed this trend lately. It's called AI, and everybody names everything AI in their company name currently. So I would say that we're currently at the top of an AI hype cycle. Because every few months we hear about a new model that's bigger, more capable, and even more impressive than the last one. Now we have GPT-5, Claude Sonnet, Gemini, and these are, you can say a lot about the AI craze we currently have, but the technology behind these are truly amazing. They are engineering marvels to just actually be able to create these and make them run, and they actually produce in some cases, some useful output. But there's one big problem with these, and they are massive in scale, and you require large data centers and clusters of GPUs just to get the next token in an input sentence. And some of these data centers consume as much power as entire cities. But the trend continues. We're now seeing a mixture of expert models, essentially even larger models, making them even more complex and requiring even more computational resources. And it's the one thing that I don't think we're really talking enough about with doing this approach, and that's the cost of everything. And I'm not really talking about the financial cost of this, although that's also, of course, truly significant, but I'm talking about the environmental costs. It's the enormous energy consumption, the carbon footprint, and especially the strain on our power grids. Norway just sold 1/4 of the available energy in the southern region of their power grids to one data center. So it won't be long before all of the available capacity is gone. And then we need to do something. Either we need more windmills, which people living in the rural areas of Norway really hate, or we need to build more water power, which is not really ideal either. And on top of this, it's also the privacy costs. Because every time you use ChatGPT and every time you send a document to Claude, and every time you even just ask your AI assistant for what you are going to eat for dinner today, that data leaves your device and then it travels across the internet. It gets processed on somebody else's server and they can do basically whatever they want with it. Of course, a lot of the big cloud providers say that, yeah, we're not going to use your data for training and so on, but there are also other providers that don't. So navigating this landscape is not really or always that easy. And we're also then at the same time becoming even more dependent on these cloud providers. Even though there's this change in basically the mindset of how we're doing cloud currently, there's this cloud sovereignty project in Europe. Europe don't want to be as dependent on the US cloud anymore. But it's not really working that well because all of the best models are currently in the US, and of course you can host some of them in Europe, but everything is really happening in the US first. So even though we're really trying, the path to actually becoming independent and getting our own compute and inference infrastructure in Europe, it's taking a long time, it's really painful, and it's super expensive. So today, I want to make the case for a different approach at this. I present to you small language models, and they are models that are meant to run on edge devices like your phone or your laptop. And I'm not saying that will be a complete replacement for the AI models that we currently have in the cloud. There will definitely be a place for them as well. But there are some cases, and usually more niche areas, where a model running on your own device will suffice. For example, Apple is doing this with all of the AI integration they're currently putting into their apps. They are actually running things on device. Some things, of course, are still running in the cloud, but a lot of things are now running on device, which is great for privacy, and is also great for the environmental impact from these data centers. And in the end, you're still consuming energy on your device as well, but you're still leveling the strain on the power grid, because you might charge your phone during the night, for example, and that helps decrease the load from the peaks of the power grid, which is really the biggest problem here. It's not that we're consuming that much power, it's all of the peaks that we're trying to flatten out. Because when you run your model on your phone, something fundamentally changes. Your data stays with you, no third party sees it, there is no internet connection required. Wouldn't it be great to just log off from your mobile network or your Wi-Fi and still be able to actually use your phone? So in this session, I'll dive into why this matters, how it works, and I also believe that small language models are becoming bigger and bigger in the future. So let's dive into it. To start from where I'm coming from, my name is Vemund. I'm 31 years old and I'm from Langhus. I am no AI PhD or anything. I'm a full stack developer, so my approach to this is the functional approach. I actually like math a lot, but I'm not going to push that on you. You don't require that to actually follow this session. I've worked in some of the largest companies in Norway, branching from Finn.no to also some of the smallest ones. I founded my own startup once. I currently don't work there, so it didn't really turn out that well. But my previous job was actually at a company called Consigli, which was an AI startup making an AI agent for the construction industry. So the aim was to reduce the costs of construction projects, energy, and embodied carbon in buildings. The company was founded in 2020, and in a world without any commercial grade LLMs. So safe to say, we were quite blown away when ChatGPT was suddenly released on the 30th of November in 2022. And that was a huge turning point, not just for our company, but basically the whole world. We had to scramble to create a RAG system before you could do this with all of the frameworks and vector databases and libraries and so on. It was a really exciting time, but it also made it really clear to us that being dependent on all of these external models that kept being changed over time, it was expensive using the API, it brought with it a lot of challenges and especially also privacy challenges. Because in the construction industry, there is a lot of trade secrets. For example, all of the tender documents that are, of course, made before for a competition to build a building, they are distributed among the companies, but they are super secret. And if that one is shared, then you lose the whole tender process. So we had some thoughts about, can we just send this through an API to the US? Some argued yes, some argued no. We ended up with, yeah, maybe. So we tried as far as possible to use, of course, the European way, but in the end, it actually became very, very expensive to use the ChatGPT API for absolutely everything. And when you're a small startup and you don't have $50 million in credits, then you have to be quite frugal about where you actually spend your cash. So what we did was something in between. At the time, it wasn't really this huge ecosystem of what I'm going to show you right now. But we did end up actually trying to run most of these models on our own without using the API. We saved a lot of costs on it, and we were also not then taking the risk of actually leaking our documents to an external service. Of course, they promised they were not going to use it for anything, but in the end, it was kind of a win-win situation for both the users of our product, but also for us, because we didn't have to spend that much money on tokens. So, what's our goal with this session? There will be a mix of how this actually works behind the scenes, but I'm also going to focus a lot on using this in practice. So just to give you a taste of what we're going to do, this is Olama. It's an application running on my local machine. There might be a demo ghost here today. There's already been one because AWS went down like 2 hours ago, and one of my examples were using AWS, so we'll see how this goes. But here we have Olama. It's using a model locally on my machine. Currently, I've chosen the GPT open source style 20 billion model. This is like a plug and play application. You just select your model, it's already set up everything for you, and it does what it's expected to do. You could also connect to cloud resources, and it works really well. It's optimized for running on Apple Silicon hardware, so using your integrated GPU on your Mac. So let's talk a bit. We have our small chat GPT or chat OpenSS. Let's see. Let's ask what I should present today. And it's actually quite capable of giving you at least some idea of what we should talk about today. Of course, this won't touch at all on what I'm actually planning, but it basically made the next batch of presentations I can send to some other conferences in the future. So copy paste, that's nice. So before we actually dive into and create these models ourselves, we need a bit of context, a bit of background to actually see how we got here today. And before I start, I just want to know like what level should I actually put this presentation on. So I want you to raise your hand if you are using LLMs in your daily work. That's almost everybody. That's cool. There are, of course, I bet there are some people in here that just refuse to use them, but that's fine. Then you might have another opinion on what I'm going to present to you. Who are using LLMs running locally in their daily work? There's a few. And then last one, who knows what quantization and model distillation is? That's like 7. That's nice. Then the rest of you will probably learn something today. The 7 of you, you can choose to stay if you want. I hope you're staying. So let's jump back to the fundamentals. Because to understand where we're going in the future, we need to understand how we got here. So something that often surprises a lot of people is that the technology behind LLMs are actually really old. The first concept, which is kind of part of this revolution through 80 years, was the perceptron. And that was basically just a simple mathematical model for creating a function approximator. So people say that you have a distribution of, you put something into this black box and then you get something out. And then you want to figure out what kind of function is actually happening inside of this box. This perceptron could be used then as an approximation to this. This is, of course, a very simple model. It couldn't do nearly anything at the time, but it was the building block that everything is built on. We jump 20 years into the future, and now people are starting to put more of these perceptrons together. So this is what we usually know then as a deep network. It was all the craze like 10 years ago, before the transformer paper. And what this basically is this is a perceptron, and these are just the input functions that we saw on the previous page here. So it's just putting a lot of these together into a network. It's nothing more fancy than that one. But the really great discovery at this time was we actually learned how to train these models without actually tuning all of these parameters by hand. Because in the perceptron era, you had to calculate, okay, I want this function to work in this way, and then, okay, if I give it this output and I want to give it this output, then I have to set this one to multiply by 5, this one to multiply by 2, and so on to just get the same output that you wanted. But in this case, in 1967, we actually figured out how to automatically train these models by themselves. And it's not really that hard. It's based on the backpropagation algorithm, which basically is taking one of these matrices. The layers between all of the nodes here are represented by a matrix. You take the derivative of that matrix, and then you figure out how you can actually change the network in how can you tune the parameters to get a bit closer to the output that you actually wanted in the end. So think of this as just vectors. These are the perceptron outputs, and then you multiply the vectors with a matrix, and then you get another vector on the as the output. It's not really that difficult if you just sit down and do the math by hand. But there was this big problem at the time, and in 1967 there was not really a lot of compute in the world. So making these large models at the time was not really feasible. Google even tried in around year 2005 and so on, just to make like these huge compute clusters made out of CPUs, but they were not really doing that great either. So think about how the computational power in 1980 was performing. But still, we tried to make other models that performed somewhat better by just tweaking the architecture. This is a convolutional network, was first invented in 1980. It's usually used for image processing and things that are, if you process an image where things are close to each other on the image, for example, a picture of an eye, there has to be a specific organization of the pixels on that image in order to make it an eye. If you just put the pixels wherever they want to be, then it's not really an eye, it's just a trash on an image. But this one then figures out how should the pixels be aligned to, for example, be an eye. And it was a step in the right direction, but it didn't really work that well. Of course, everything just depends here on the Moore's law, where if you just throw enough compute at it, then it will finally work in the end. And we are still not, or we haven't reached the end of Moore's law yet. We kind of like switched a bit over to the GPU world, so we are enhancing our compute scaling that way, but we're still getting there. In 1992, we actually made something that looked like a transformer. So everybody believes that this was a huge invention in the 2017 by Google, but there was actually this architecture in 1992 that really resembled what ChatGPT looks like today. It was this concept of you encode the input, you create one token, and then you feed the whole thing into the same network again, and then you create more tokens as you go along. And finally, attention is all you need. The famous paper by Google in 2017, this was basically the final piece of the puzzle. And as I told you, it was kind of the technology was already there, but they actually figured out how to use it correctly. At this time, they had actually switched over from their compute cluster from CPUs to GPUs, so you could actually do something useful with all of that compute power. And this was then the final piece to making these GPT models. And from there, they just kept throwing more and more data at the problem and throwing more compute at the problem as well, and then it suddenly just solved itself. So nobody really noticed when GPT-1 was released and GPT-2, but then suddenly GPT-3 became actually usable because it was made into a chat interface and it was actually producing kind of okay sentences, which was super cool. So this is our background. How did we end up then with models with 685 billion parameters like DeepSeek, when basically we didn't really have that much compute before? We suddenly had a lot of compute, and then everything became super big and you had to have a whole data center to host it. But now the trend is kind of turning. We want smaller models, and there are a lot of ways to do this. So we will cover two different methods in this talk, which is quantization and also distillation. And the first method here is basically a method where you take one of these super large models, for example DeepSeek, and you just shrink the actual size of it. So it might actually then fit on your video card or your compute cluster or whatever you actually want to run it. And so let's look at how we do that. These networks that I mentioned, these deep neural networks, they are made out of matrices. And in this matrix, you have numbers. They are usually encoded as either float 32 numbers or float 16 numbers. And that's required because during these training runs, they vary a lot, like the weights in this matrix, they change a lot during the training period. But then when you actually trained your network from scratch, somebody just tried cutting off the end of this very precise number and see what happened. And it actually worked quite well. There is probably a lot of number theory behind this, but as I told you, I'm not the math guy, so I came to this from the functional approach. But the whole deal is take this matrix of numbers and basically just compress them into a smaller format. And you still run the same network, and it actually performs quite well. So the point here, usually we go from float 32 to either int 8 or actually int 4. to give you some perspective on how large the input space for a float 32 is, that's 4.58 to 10 to the power of 38. That's a lot of numbers. And we're going to compress it down to int 8, which is 256 numbers. So it's actually crazy to think that this actually works. But the way you do it is you take this network, and of course this is the matrix that we're talking about. This is just a matrix of numbers. It's nothing fancy. And then it looks like this, actually stored on disk or in lists or whatever. So you take this matrix, you convert it by first figuring out, okay, how big is the scale here? What's the biggest number, either negative or positive? In this case, it's 5.64. So you take the maximum of the matrix, because that's like your limit. You don't want to always go from, what was it, 5.4 times 10 to the power of 38 and to minus the same number. We'll do it locally so that at least some of the numbers here don't end up as only zeros. You also calculate the scale factor, which is a number that's required to turn this int8 matrix back to a float, or about the same range again. So we'll do the calculations. What you're basically doing here is mapping each of these individual numbers into what would it be if it was an int8 with these boundaries. So going from minus 5.64 to plus 5.64, then the highest number would be 127, because that's the highest number you can have as an int8. And around 0, that's the first number, 0.34, that's about 8. So you get like some kind of nice distribution. And what you then do, you take this quantized matrix and you put it back into the network. So you basically just replace it. Also, there are some details here with the scale factor to make it actually the same number again. Otherwise, your network would probably be crazy because it expected a number between 0 and 1 and it got 127. That's not really nice. But using the scale factor to get it back to the number it would normally be, it works. There are some problems with this. And for example, that's if, say that your number wasn't 5.64, it was 1000 in this case. Then you would end up with a matrix with zeros, and then you have one big number and one minus one, because 0 or minus 4.7 is just enough to actually get some output other than 0 in this case. So the reason for this, why it actually works, is, and why we're actually doing it, is because doing math with ints is a lot faster than doing math with floats. So you shorten the number of bits that's required to actually run the network on your GPU, but it's also scaling it in a factor of like 30 or 40 times, because doing int computation is super effective on GPUs, while floating point requires a lot more computation to actually just get an output. So even though we are actually putting the same matrix into the network again, it's as many numbers as you initially had, they're just smaller. And you even multiply with the scale factor when you're done. That's 20 times faster than just doing the floating point operations that you had to begin with. So to show you some examples of this, then I hope, who here has actually been on Hugging Face before? Nice. So for those that haven't been here, this is Hugging Face. This is your go-to shop for all open source models that you want to use in the future, and also you can run them now. It's integrated with Llama and Ulama and everything I'm going to show you afterwards. But here lies all of the open source models that we have. For example, the Qwen 2.5 coder, 32 billion parameters instruct. So this is an open source model. It has 33 billion parameters, and the size is about 65 gigabytes. That's including everything else inside of this repository. So I would guess the model itself is probably like 30 gigabytes or something. I don't have a graphics card with 30 gigabytes of memory. So instead, we could look at this quantized model. So this is the same model. It still has 33 parameters, it says here, but it has all of these versions of it. So In our case, we made an int8 quantization of this matrix. You can also do, for example, 2-bit, which is even smaller, so you have basically a 0 or a 1. And it actually works that as well, which is crazy to think about. Then you get the size down to 12.3 gigabytes. Our example with the int8 is still 34 gigabytes, so probably here we could go for a 4-bit quantization, for example, which is 18 gigabytes. And just using the RAM on my computer, I could probably just fit that one in and then use it locally for development or just having a chat application. So there are possibilities of, because I had no chance to actually run this one without a huge compute cluster on the side, but there are ways. So let's look at the other method for actually doing this, which is called distillation. And this one is not really looking that much into how the network is working. It's more how is the network performing and how is it behaving. Because the main idea behind this is that DeepSeek, which is a model with 685 billion parameters, that's 600 gigabytes of memory required to actually run it. Not really that feasible, but it's basically good at absolutely everything. So it's an all-around good model. But still, I am only interested in generating tips for home interior in my shop, for example. So all of the questions that I will feed into it will be about home interior. And then I want my model to behave well when I'm giving it this kind of output. If I give it something else, then I don't really care if it's a bad response to it. So perhaps only I need some parts of DeepSeek for this. So how can we do that? If you remember, this is the transformer architecture. So we have our DeepSeek R1 model. As previously mentioned, it outputs just one token at a time, and then you feed that one into the next run through the model, and then you generate a sentence that way. But that's not technically true, because the output of a transformer model is actually a probability distribution. So it actually gives you a probability for all the possible tokens or words. Let's not go into the token versus word debate, but let's just say it outputs a word. So it actually gives you the probability of this word coming after all of the previous words that it's been fed. So all of the different tokens then get a number between 0 and 1. And then this is then the output distribution of this transformer. So given the start of a sentence, I am, then the distribution looks like this. If we take another model, the Llama 3.2 model, then you can see that this is another distribution. It does not match DeepSeek. And that's because these are different capable models. They've been trained in different ways on different data, and if they were similar, then they would behave the exact same for all inputs. But DeepSeek is good at very much, and Llama 3.2 will, not really that good at everything, but it's still a nice starting point. So what if we could just teach the Llama model to behave a bit more like DeepSeek, so that we could instead run this Llama model locally and get kind of the same performance as our DeepSeek model. So we'll set up a teacher-student relationship here, where the teacher is going to teach the student how to behave. The way it's doing that is when you're training a network, then you give it some input, you get some output, and then you say this output is correct or is wrong. And then the backpropagation algorithm that I mentioned, it calculates how can the network be changed so that it performs a bit better next time. And basically you do the same thing here. You put some input into the Llama model, it gives a probability distribution, and then you put the same data into the DeepSeek model, and it also creates a probability distribution. And then by comparing these two, because the DeepSeek one is that's the one you want, then Llama knows that, okay, if I just correct myself in this way by backpropagation, then I can make something that looks a bit more like the distribution out of the DeepSeek model, which is great. So then you just do this 1,000 times or 100,000 times, or probably a few million times. Then it slowly begins to be a bit closer to the DeepSeek model. But the point here is you cannot just feed it anything. As I mentioned, our whole example was about home interior questions. So you only feed it questions about home interior, because the 3 billion model is not capable of understanding or representing everything the DeepSeek model can, but it can probably be tuned so that it actually matches DeepSeek quite well in this one specific area. So then you have the benefit of having a 3 billion parameter model. It behaves as DeepSeek in this special case, and then you can even quantize it even more to take even less space, which is great. So then you can probably run it on your phone. There are applications that can run large language models on your phone. I suggest you try them. They are not that great, but it's getting there. So to then again go back to Hugging Face to show you a bit how it actually looks in this case. This is the DeepSeek model. As I mentioned, 685 billion parameters. This is the largest open source model there is. I think Llama 4 might be a bit bigger, but this at least blew the world when it was released, because this is not even a company that's living off making these AI models. It was just something they did, and then they released it because they use something similar inside their own company. Yes, so of course there's a lot of information about it, but here it's already been done for us. You don't need to do this process yourself. We have these different versions of the model. DeepSeek R1 Distill Quen, that's another model, 1.5 billion, Quen 7 billion, Llama 8 billion, and so on. Of course, if you take the largest student model, then it probably will perform the best, but it might also be overkill. If your area of expertise is really narrow, then you might also do just as well with an 8 billion parameter model. Technically, you could also start with just an empty network and then try to train it, but that's a lot harder and requires a lot more compute. So you always take one of these models that already exist, and then just fine-tune it to behave as the bigger model does. So let's have a look at some of the examples. So what can you actually do with this? So now we have two methods, and as I've shown you, everything is already done for you. You don't really need to do this yourself. So we can have a look at some of the tools that we have. The first one I want to talk a bit about is llama.cpp. There's a lot of llamas in the LLM world, which I love, that we as developers, we can just give funny names to things, and nobody comes after us and say that we can't really name things like this. If you worked in the construction industry, then this would definitely not be allowed. But as developers, we can get away with it. So the Llama CPP project is great. It's a bit more kind of bare metal than some of the other solutions that we will have a look at, but it gives you also a lot of flexibility in what you actually can do with this. So this is a tool that you can use then to locally quantize a model. The way you do it is you just download a model from Hugging Face. I don't remember the command correctly in Llama C++, but you just run a command on it, and then it automatically quantizes the whole thing. So you get a model out, you take a model in, you get a smaller model out. It's great. It can also be used to host endpoints for models running locally. So say that you have your Llama model and you want to make an OpenAI compatible endpoint for it. And that's a one-liner in Llama C++. It automatically tries to find the GPUs on your computer, so it allocates those to your model. And you get an endpoint where you can set up, for example, the SDK for OpenAI to point to your local host instead, and you can use it as you would normally do. In addition to Llama C++, we have Ullama, which was the thing I showed you in the beginning. This is also a great project with a very nice logo. This one is more plug and play. So as I showed you this example here, you basically you can choose these models, and this is because it's only running on Mac, so it has all of these pre-trained models for you. It behaves well, it downloads them automatically, which was really fun doing on a hotel room here, because it took like 8 hours or so I was a bit anxious if this model would finish before this talk. And you can also use it to run a local server hosting this model. So say that we have Let's see. For example, we want to run a Llama 3.2 model locally, then we just do it. And now you can talk to the same model as I showed you in the interface. So hello world, what should I present today? And it will probably give me some ideas. This one, of course, has another prompt than the graphical user interface one, because this one can only generate text. The user interface can actually give you some formatted output, but you get the gist of it. And then the final thing that I really think is coming up next is actually that you can run transformers in the browser. So there is actually no need to run these models on your backend if you can just push them out to the consumer and you can actually use them in your web browser. It does come with a caveat, and your mileage may vary. They're not that good yet, and they only run on CPU because they are compiled into WebAssembly. They're not running on any GPUs at all. So now I got the Qwen 1.5 0.5 billion chat model. Let's see if it actually provides some nice output. Hello world. Hello. Nice. So then this is a model then that was just downloaded into my web browser. It runs it using WebAssembly, and you can actually chat with it. What should I present today? Yeah, pretty much the same thing. So not that far off, but it's not really great. And you can't really get that much power out of a 0.5 billion chat model, but it's getting there. Because what's coming next in this world of small language models? Let's see if I can just get my presentation back. That would be nice. There we go. Where are we headed? As I showed you, the story about LLMs is starting in the 1940s, but it's really exploded in the last 5 years. Naturally, because it was actually then becoming useful to make them. And now everybody tries to put their savings into stocks on AI, and we'll see how that goes in the end. But at least there is a hype cycle here where everybody's hopping on the hype train and publishing new findings, new reports, new architectures, and trying to beat the state of the art. But there is this kind of trend where the problem is now that we are basically out of training data. So OpenAI, Google, and all of the large providers, they basically have vacuumed the whole internet. And they've basically taken all of the written language that we produced since the internet was started. So you can't really just make more training data up. So we are starting to hit the point where it doesn't really work by just adding more data and more parameters and more compute, because there is no more data. And then it doesn't help to produce more or put more parameters into it. So then we need to be smart and make more out of the things we have. For example, by distilling these large models or training them in completely different ways. I mentioned some mixture of experts. Instead of having one large network, you might have multiple small ones, like I mentioned with the fine-tuning of the distillation process. You might have many of those for specific tasks. And yeah, they are kind of running out of ways to create more of this training data. And OpenAI is still on the verge of making artificial general intelligence. I think the last piece of the puzzle they need is to create erotica for adults, so that they can then solve the problem of artificial general intelligence. And lastly, web GPUs. As I mentioned, the 0.5 billion parameter model was awful, really. But if you start to use one of these new standards that's coming called web GPUs, where you can actually utilize your GPU in your web browser, then you could actually fit a 12 gigabyte model into your web browser and use it on your consumer device instead of having to host the model yourself. So let's see. The future is bright. There is maybe some less focus on all of these big models and instead trying to push them down to consumer devices. So we'll see. Thank you. free to leave, but if you want to ask some questions afterwards, then you can just stay and have a chat.